Go. Hello and welcome to Calculus 3 section 13.1 on vectors in 2D. So, in order for us to do multivariable calculus and vector calculus, in order for us to do physics and engineering, we need to talk about vectors. Now, vectors are mathematical constructs. They do not exist. It's something that we have as a concept that we can use to portray a reality. Just like number 8. You don't see number 8 walking down the street, right? It's a mathematical construct. It's the abstract that you have in your head. And if you walk up to anyone and just say 8 and you leave, they're going to think you're crazy, right? Because number 8, right? We all understand what it means. It shows the quantity of 8. But you would like to know 8 of what, right? Why did this strange person just walked up to me and said 8 and left? What do you mean 8? Is it 8 p.m.? Is it 8 a.m.? Is it 8 the date? Is it 8 cars, right? What is going on, right? What is that number 8? So number 8 as number 8, we understand it shows quantity, but we also like to tie that to something in order for it to make sense. You can't just say 8 and leave. So vectors are going to be in the same boat. You don't learn vectors for sake of learning vectors, passing a test, and being done with life, right? Vectors will portray, right? They will describe, they will do something with the tangible things in nature. So you can describe a force with a vector. You can describe various, so the velocity, right, the speed is going to be the part of the vector. Speed is not a vector, velocity is. Acceleration is another one of them. Describe with vectors. And by the end of this course, in the last chapter, we're going to talk about vector fields, which is infinitely many vectors pushing, let's say, the particles of air forward. We call that wind. You have the currents in the ocean, which is, again, the particles of water, molecules of water, moving in a certain direction. So you guys have two-dimensional vectors, three-dimensional vectors, and then you have groups of vectors, right, which we will, as a function later on, define as a function in the vector field. So you will have electric field, magnetic field, gravitational field, and all other fields that are out there. So we get to understand the nature around us using these mathematical constructs which actually don't exist. The same thing you've been doing with numbers. Now, vector is a higher order creature than what the number is. See, with a number, you just have a value of a number. The numbers show quantity. They don't exist, they show quantity. So there's only one quality about a number, which is its quantity. Yeah, go ahead and unwrap that sentence. So when you say a number, you immediately are thinking about an entity, a number, that will show some kind of quantity. So you say, think of a number, you might think of number 13, right? And we all understand what it means. And then you can also say, well, I'm thinking of 13 trees or 13 cars or whatever else. Now, vector is going to be I don't want to call it one dimension stronger than a number because these are all part of tensors, which is the next level math. Vectors have two qualities about themselves. One is the same as number, which is what we call magnitude, which is the quantity. And then they also have direction. So a number is only described by the value it has, which is, right, how large the number is, which is the quantity to count things. Vector has that quality as well, and in addition to it, it has direction. So certain phenomena in nature are better described by vectors than by just numbers. And as I said, one of them would be force. Force would have the strength and the direction in which it's applied. right? So we can have the very simple, the direction is either strike the board or strike the desk, right? So that will be the direction. Which direction am I applying force to? And then you also have the strength, right? You can have this one and you can have, right? So depends, so the strength with which you would hit would be, or push or pull, that would be the number, which we will call magnitude. We'll write all of that down, obviously. And then you would have the direction in which you swing, and that would be the angle. And then we are going to have, for 3D, right, we are going to have the same deal, but that's the next lecture. So vectors will be described by these two parts. One is the magnitude, and the other one is the direction. So vectors have magnitude and direction. Now, we can understand magnitude as the length of the vector, which will give that numerical value. How fast are you going? That's the speed, right? The direction in which you are going plus the speed makes up velocity. You don't see velocity limit 65 miles per hour because in the common sense, right, we should all be driving the same way on the same side of the highway, right? I mean, obviously, occasionally you will have someone driving the opposite way. You all seen those people when they miss the exit, like it's the end of the world, right? If they miss that exit, and if they don't back up on the highway to take that exit, if they just go another 2 miles, they're gonna fall off the edge of the earth. And anyway, so magnitude is the length, is the strength, is how fast you're going, and then direction is going to be the angle in this 2D case, which is which way the vector points. So the notation for the graph of the vector would be, you can use obviously XY plane. You will join 2 points. There is the initial point, which is usually in the origin. And then there is a terminal point, which is the point where the vector ends. And the direction of the vector is always from initial to terminal point. So it has a beginning and it has an end. So now you will also describe this vector in its x and y. So we have x and a y. And if we call this vector u with a little arrow above, you always have to put this arrow, because the difference between the variable x and the vector x is just that arrow. In the books, they use bold letters to describe vectors, but what is you have a u and then you have a bold u. Are you really going to spend time to make that bold every time and make sure, right? So it's much faster for us for exams and notes and so on when we write to put a little arrow above, which signifies that u is a vector. It will have the spiky brackets and we'll have the x comma y, which are the lengths from the diagram there. And we'll just put that. So when you take a look at the terminal point, in this case, the terminal point is at 4, 3 on my diagram. That would create the vector u to be 4, 3 within the spiky brackets. You have your spiky brackets on the keyboard right next to letter M, and your parentheses are on 9 and 0. So those are obviously different notation. So if you are using regular parentheses, you have notation for a point, which is a terminal point. If you are using spiky brackets, you are talking about the entire vector, which is the black line stretching from the origin to the 4, 3 point. I'll just say point 4, 3, and that's not the same as a vector 4, 3. So the point is just the point, the location in space. The vector is the entire length of the arrow there from origin. Now, one important thing is to say that vectors are free to move in space. And this means that your vectors do not have to emerge from the origin. They can start at any point in space, and they will take 4, 3 as a unit from there. So to have this vector u somewhere else in a coordinate system, you can pick a starting point. Let's say you pick this starting point, which in this case is 1 and negative 2. Your job is to go 4 units in x, 3 units in y, and this will still be vector u. Even though this diagram doesn't look the same as the previous diagram, your terminal point is 5, 1 now. When you look at this, it's still the same vector, because the vector will have, this vector and the other vector we had up there has the same length and the same direction. So now that gives us another very important realization about vectors. Two vectors are the same if their magnitude and direction are identical. It doesn't matter where that vector is in space. So you can think of anything as a vector. The pen that you are writing with can be thought of as a vector. If you use it properly, it will work. If you use it the wrong way, it doesn't work. Just try to flip your pen and try to write. It will not work. Why? Direction is wrong. All right? So the pen that you are using is directional. Right? It works only one way. And you need to be perpendicular to the page. I mean, if you turn the pen sideways and try to write, it will not work either, right? So there is a very narrow kind of amount of angles in comparison to, and how many angles would not work in, right, that you can use to get this pen to work. So that being said, your pen, which can be thought of as a vector, is free to move in space, which means that, right, the pen is produced in a factory somewhere, in China or Malaysia or whatever, and then shipped over across half of the earth because we have no capacity to produce anything. And then that pen, imagine if the vectors were not free to move in space. That means that the pen was made in that factory and has to remain in factory forever. Can't move anywhere. Right? So vectors are free to move in space. You are a vector. You stand up, right? Let's say you are, I don't know, 5'5" height. Well, there's your magnitude, and what's your direction? Upright. At some point in the night, your direction is going to be horizontal. Still the same magnitude. It's going to be a different vector, because when you're standing upright, well, most people are conscious, right? When you are horizontal, while you sleep, you are unconscious, right? It's two different states, so two different vectors, right? So the idea is that vectors are free to move in space, and in order to have two vectors to be the same vector, those two vectors have to have the same magnitude and the same direction. Now, another thing over here is what we realize from this diagram, other than the two vectors are the same, we realize that there is a formula that we can use to calculate the vector if you have terminal points. Because if you call these 2 points, point P and point Q, by subtracting their coordinates, you guys can come up with the vector U. So we say PQ, vector PQ, in our case that was vector U, is going to be subtract terminal minus initial for X, and then terminal minus initial for Y. So terminal for X, sorry, so 5 minus 1. And then for terminal, it's 1 minus negative 2. So that vector PQ, in this case, is 5 minus 1 is 4, and 1 plus 2, right, 2 negatives, is 3. And we see that's our vector U. So in order to find the vector, so now we can put that, in the formula if you want to. I'll just put any 2 points anywhere, P and Q. And this you can regard as a formula. So vector PQ, where Q is the terminal point, look at the arrow, is going to be given as XQ minus XP, comma, YQ minus YP. So this is the terminal minus initial as a formula to find the vector that stretches between 2 points. Again, very important to know which point is terminal point. Terminal point is always listed second. Now, the next concept coming out of this is that PQ is not the same as QP. Can anyone tell me why? They're the same length. Yes?
Because of the direction.
Direction is opposite. Direction is opposite, so because of the direction. Remember, it's really important which way you drive on 78. Otherwise, you will get erased. All right? So direction is important. And the matter of fact, we can fix this and make it into a formula because these two vectors will actually just have the opposite direction, so you can just add the minus sign in front. That's what means that the vector has the same magnitude and opposite direction. So one vector is just equal to the negative of the other. If you are to swap P and Q, you will just get the negative values here, right? If you take a look at 1 minus 5, it creates negative 4, and then minus 2 minus 1 will create negative 3. So you will get minus 4 minus 3. So that's completely opposite for QP. So this is not the same, so that will create the formula that PQ is equal to the negative QP. Now that is something that the comment over here, they have the same magnitude and opposite directions. They have the same magnitude and opposite directions. So these are some basics of vectors. they are higher creatures than numbers. The number is a part of a vector in terms of a magnitude. So that's the size of the vector, like the size of a number. Are you talking about number 6, or are you talking about number 8, or are you talking about number 10? 6 is smaller than 8, is smaller than 10, right? The vector can have a length of 6 units, or 8 units, or 10 units. So 10-unit vector is longer than the 6-unit vector. The force of 6 newtons is less than the force of 10 newtons. The speed, right, which is the magnitude of the velocity, the speed of 60 miles per hour is larger than the speed of 40 miles per hour. So magnitude is the number. Direction adds another quality to the vector. Now vectors, because they are numbers with directions added to them, can be added, subtracted, and also scaled if you need to. So let's do vector scaling first. Vector scaling. If I have a vector that is 3 units long, so magnitude is 3, I can create a vector that it's twice as long. So this is a vector u, this one will be 2u. Magnitude is 6. So what this number that you get to multiply vector by is doing is simply making the vector longer, or if you use a fraction in there, makes the vector shorter. You have to use a fraction between 0 and 1. Like a half cuts the vector in half. A quarter takes a quarter of a vector. So you can scale. Here we can draw one square only and just say 1/3 of u. So magnitude is 1. Magnitude 1 vectors are very important. We'll define them as unit vectors, and they will stick with you for the rest of the course. So vector scaling is very simple. I'm just going to put in parentheses over here in blood. Vector scaling preserves direction, right? You don't get to change the direction by changing the size of the vector. You only change its size. That's what you're doing when you push your gas pedal, right? Your gas pedal doesn't turn your car left or right, right? The direction of wheel motion. It only adds to the speed or brakes, right? So technically what your gas pedal does is this, and what your brakes are doing is this for the speed. So vector scaling, direction stays the same. That's important part. And we will actually use that, which is why I wrote it in red, later on for directional derivatives and stuff. And projection, tomorrow we'll do projection, and you guys will see that we have to preserve the direction. Good. So that's vector scaling. Now we can add and subtract vectors. And in notation, that's very simple. All we're going to do is we are going to add x components and add y components together. So if you have two vectors, vector u plus or minus vector v, so you want to add two vectors together. Does this make sense? Of course. If something is too heavy for you to pull or push, you get a buddy, right? In that case, you have two vectors that together are pushing. Again, the push is the push from your hand, which is the force, right? Which is going to have a greater impact than if you're alone, right? That's why Obi-Wan Kenobi is infinitely wise. He said Anakin will get them together, right? And then Anakin didn't listen because he was too young and got almost killed. So, right, the Force push, do it together, right? Two people. So now what do we have? You are working on this component-wise. When you add a vector plus another vector, you are going to get a vector, right? So the answer will be a vector, which means we need our spiky brackets. It is going to be the x component of vector u plus or minus x component of vector v, comma, y component of vector u plus or minus v, y component of vector v. So this is official formula. If you are not following all of these subscripts and stuff, then we just follow this with the example. Our vector u was 4, 3. What's vector v? What's vector v? 6, 2. Thank you. So, following this formula, 4 plus 6, comma, 3 plus 2, the total of 10, 5. If you are subtracting these two vectors, it's 4, 3 minus vector 6, 2, and you are getting 4 minus 6, comma, 3 minus 2, and that would give us negative 2, 1. So we can scale vectors, we can subtract vectors, and add vectors. Now, guys, subtraction is not actually something that we need at all. Because remember what we said, that the vector PQ is the same as the negative QP. So in that sense, this negative is like multiplying negative 1, which is scaling. So u minus v as a vector, keep a note of this stuff, is going to be u plus negative 1 vector v. And that's just the opposite direction of vector v. So if you are to graphically subtract vectors, you will draw the opposite vector v. So this is a cool fact. Obviously, you will just subtract coordinates and be done. You are not going to, worry about this particular aspect. But it's important to know that subtraction doesn't exist actually at all, not even with numbers. I was lucky to have a really cool dad who, when I was a kid, I didn't even know numbers yet. Those cubes with numbers and letters on it? I had that as a kid. He went ahead and some of them with a Sharpie added minus signs for some of the numbers. So now, for me, subtraction as the operation doesn't exist, and actually it doesn't. Because what you are doing is you are adding, or you're always adding. What is 5 minus 3? It's 5 plus negative 3, which is 2, right? So that is a really good way to think about for vectors as well. There is only vector addition. Graphically, there is only vector addition, and you're adding a vector with the opposite of another vector if you want subtraction. So if you want the two vectors added, which were 4 and 3 and 6 and 2, so u equals 4 and 3, don't forget the arrow, and v equals 6 and 2. Graphically, so now we'll need a larger coordinate system here because we have to go out to 10. We have x and a y. You will start with your vector u, 1, 2, 3, 4, 1, 2, 3. So this is your vector u. Now, at the end of that vector, which is the terminal point of vector u, you are going to count 6, 2 for vector v. 1, 2, 3, 4, 5, 6, 1, 2. This next vector, which I'm going to put blue, let's say, is vector v. Remember that vectors are free to move in space. I can draw this vector v wherever I want. Well, I decided to draw that vector starting at the terminal point of u. So now these two vectors, right, are linked. And if I draw the vector from the origin, which is the initial point of u, to the terminal point of v, I will get u plus v. Now, if you go and count the number, you are going to end up, you must end up with 10, 5. Otherwise, we broke mathematics and we can all go home. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. The end point is 10, 5. And the actual red vector that stretches from 0, 0 to 10, 5 is spiky 10, 5. Spiky brackets, right? So that's the way to add. You can add graphically. Now we are going to add, well, subtract through addition again using the opposite. Is draw big. If you're not an engineer, I'm not sure why you're here. Right? It's Calc3. So we are going to go 1, 2, 3, 4, 1, 2, 3, and vector u is there. Now, remember how your vector used to go 6 to the right and 2 up? Yeah, that's your vector v. Your vector v is 6, 2. Your negative vector v that you will be adding to u is going to be negative 6, negative 2, because you are multiplying that negative 1 to each of the coordinates. So your blue vector now is going to go the other way, which is 1, 2, 3, 4, 5, 6 to the left, 1, 2 to the bottom, and then since you will be adding this, so now the blue vector is negative v. So you have the black vector. I'm going to move this u underneath. You have the black vector, which is the u arrow, and you have a negative v. Now when you connect the initial point and a terminal point, you get u minus v. And if you read the coordinates, it's negative 2, 1. Magic. Right? Negative 2, 1. So this vector here is vector u minus vector v, which we got by saying u plus negative 1 times vector v. Subtraction doesn't exist, actually. All right, it's just addition. That's it. And what's multiplication? It's fast repeated addition, right? What's 3 times 5? 3 plus 3 plus 3 plus 3 plus 3. It's just our lazy way out, because we're lazy. That's why we memorize. You make a trade-off, right? Instead of saying, okay, 7 times 8 is 7 plus 7 plus 7 plus 7 plus 7 plus 7, right? You make a trade, conscious trade, to memorize that 8 times 7 is 56. Rather than 7 plus 7 is 14, plus 7 is 21, plus 7 is 28. You can get there. You will get there eventually. But because we are lazy, we say, we'll just do the multiplication instead. Right? So, and now you know that subtraction is also boo-ha, because all you need to do is to add an opposite number. So your whole mathematics just crumbled now down to one operation. Like, how hard can it be? Come on. All right. First time you go home and say, I learned less. Right? It's like, you learn new math? No, I actually learned just like I don't need any of the stuff I learned. No need for subtraction, no need for multiplication, no need for division. Exponents, what is that? That's uber fast addition, because exponents are repeated multiplication, and multiplication is repeated addition. So exponents are uber fast addition, actually. So you just go out and figure out how much of addition is done in, 2 to the 4th power. How much adding you're actually doing. Well, you break it into multiplication and then break it into addition, and it's just going to be revealed eventually. Well, that's that. So now that we played with coordinates, note that I never gave you formulas yet for magnitude and direction. I just said they exist, and I played with coordinates. I wanted to get this most basic and simple idea that there is initial terminal point, you can subtract them, the vector is going to look the same as a point, except it's going to have spiky brackets and you can move it anywhere. Now we can write down the formula for magnitude, which would be absolute value u, so that's the notation. In some cases they put double absolute values. You're going to see in linear algebra and so on. It's going to be the Pythagorean theorem of x squared plus y squared. And direction, theta, is the inverse tangent of y over x. So I'll put this on a cloud so you have access to it. And if you just draw a quick diagram, all of this immediately must make sense. Otherwise, it's a wrong course. If I have a vector u, and I have its magnitude, which is the length of the black line, when you drop the vertical down, this is your y, this is your x, this is your angle theta with the positive x-axis. So, Pythagorean theorem will tell you that absolute u squared is x squared plus y squared. Move the square root to the other side. Ignore the negative because lengths are only positive. And then you have the tangent of y over x of theta, and then get theta alone by moving inverse tangent, right? So magnitude and direction are simply these two formulas that you should be familiar with. And to write down, and if you belong to the honors section, you will have to prove at least 2 of them on the first exam. And they all prove the same way. So I'll demonstrate on one, and a few of them are also done in the book. I'm just going to log in very quickly because 10 of them I don't want to forget any. You have distributive, you have the commutative rule, you have a whole bunch of stuff. Multiplied by 0, and 0 vector, and multiplied by 1. And so there are 10 rules that we are going. So properties of vectors, and these are going to be cut and paste for 3D vectors. By the way, vectors can live in any dimension. They are not just 2D and 3D vectors. Conceptually, in mathematics, you can have the nth dimensional vector, which is the topic of linear algebra. It's dealing with n-dimensional space vectors. So, which is why that course is so damn powerful. We are used to third-dimensional world around us. We are used to two-dimensional world as a surface of the paper you're writing in. So those are the 2 dimensions, right? Two spaces that you guys are used to. But if you want 17 dimensions, there is no reason not to have 17 numbers between spiky brackets. It's okay. It's just 17-dimensional space. We don't currently have a use for it, but mathematically, it's possible. there is always that great disconnect between mathematics and technology. It's about 200 to 300 years gap of what math does, and then physics needs to catch up, and then engineering catches up, and then consumers, right after the military is done with or space program is done with whatever they have, then consumers get it, right? Every single major advancement we have in technology was first in the hands of military and in the hands of space research or something, and then eventually be touched. Internet as well, right? It was. So let me just really quick get here. Should have done this. Every day, when this website is not asking me to pick out the storefronts, traffic lights, and crosswalks, I'm a happy guy. Because most of the time there's that one picture that in a corner has like 3 pixels of a car, and then it's like, do I click this one or you don't? Because if you click it and it's wrong, then you have to do another one. Oh. It's the first world problems, trust me. I don't have to deal with hunger, so. But when that picture comes up for me to pick, whoo. The first thought, if I take myself out right now, I don't have to deal with this. Right? That's the first thought that grows to, right? Anytime when something insignificant happens, that's the first thought. Where is this thing? Come on. There we go. Finally. Page 811. So, properties of vector operations. Vector addition is commutative. So, vector u plus vector v is the same as vector v plus vector u. Same as numbers. Number 2, associative property. If you have 3 vectors, it doesn't matter which order you add them in, just like when you're adding 3 numbers. So you can associate u with v and then add w later. Or you can add v plus w first and then add u later. Number 3, v plus the 0 vector. Guys, there is a 0 and then there is 0 vector, and they're not the same thing. Is going to give you vector v back. Number 4, if you add a vector to its opposite, you will get the 0 vector. Number 5, distributive property number 1, the constant can be distributed to each individual vector you're adding. So cu plus cv. Or if you have 2 constants, a plus c times vector u, that's going to be au plus cu. Okay, now, if you multiply 0 into vector v, you will get the 0 vector. And here I'll write it in blood. 0 is not the same as the 0 vector. 0 is the location on the number line, and the number line is one-dimensional entity. So you just have a number line, and that's here, 0. 0 vector is the multi-dimensional vector of 0 length. So it sits at the origin. You cannot tell me that the origin of the xy is the same as as 0 on the just x-axis. It's not the same thing, right? So 0 vector is a different creature than the number 0. So again, the arrows that we put are not there for decoration. They serve the purpose to distinguish variables in a one-dimensional realm from a multi-dimensional vectors, which would have direction in addition to their lengths, which are magnitudes. You can think of it this way. Numbers, 1, 2, 3, 4, 5, they only have magnitude, which is their size. They have no direction. Okay, constant times 0 vector is 0 vector. Number 9, 1 times vector v is vector v. And finally, number 10, associated property for scalar multiplication, a, c, vector v. You can multiply a and c first and then multiply that result into a vector v. All of these properties are proved the same way. Some of you expressed the wish to have more work in this class by signing up for honors, which is great. So for you, because you are going to have extra problems which are proofs on your exams, let's say proving number 7, 0 times v equals 0 vector. Well, let vector v be vector in 2D, v1, v2. You can call it vx, vy, va, vb, whatever. It's just there are x and a y component to it. So 0 times v1 comma v2 is equal to, you know that the 0 now multiplies each one of these. 0 times v1 comma 0 times v2, which is 0 times v1 is 0, 0 times v2 is 0, which is a 0 vector. So you show this way that the left side equals right side through running this calculation. So now for all of the other proofs that you guys have, all 10 of these, I think 2 or 3 are worked out in the book, and here's the extra one. For all of them, you will write u as u1, u2, or ux, uy, whatever is easier, whatever you want to. And you will just run the calculations along, getting the right side in the end. For something like number 10 or number 5, your goal is to massage both sides until you end up with the same expressions on the left and the right. For instance, over here, the first step is to have CV1, CV2. That's the first step. And then the second step is ACV1, ACV2. Over here, you get ACV1 immediately and ACV2 immediately. So the left side will have 2 steps, the right side will have, and then the expression on the left and the expression on the right would be exactly the same, which proves that line. So some of these are 2 lines, some of these are 3 lines. They are very simple and quick proofs. And again, these proofs are featured as extra problems if you want to sign up for honors within this class. If you want to sign up for honors, just let me know. It will have the honors added to your on the transcript. So it will say Calculus 3, Math 251H, honors. So you have extra lab, extra exam problems, extra problem on the project. So it's just, right, you do everything else what everyone else does, so that's 100% the same, and you just have extra stuff on top for that. All right, so we have this, and now the grand finale of this is the unit vector. And yes, I wrote the title in red. Unit vector is going to be your friend. Unit vector has a magnitude 1. Whatever the direction, magnitude is 1. So unit vector, so number 1, magnitude is 1 unit. The notation is u hat. So instead of an arrow, you know it's a vector. It is a vector. But instead of the arrow, we are going to put the hat. So that's how you know that something written is the unit vector. And the way to calculate this puppy is going to be your vector u divided by the magnitude of vector u. So this is the formula to compute vector u. So magnitude is 1 unit. So the cheapest example is to calculate unit vector for u, which is 3 and 4. So when you need to find the unit vector for the vector 3, 4, you have to find the magnitude first, which is the square root of 3 squared plus 4 squared. We are using the magnitude formula. And once you have the magnitude formula, that's 9 plus 16 square root of 25, which is 5. So now u hat, which is the unit vector, is the original vector 3, 4, divided by magnitude 5. It will divide each of the coordinates. This is like scaling, which is times 1 over 5, right? So the unit vector becomes 3/5, 4/5. So that's the unit vector. That's what you were looking for. Now, this vector is very important. This vector only has direction. Its magnitude is 1. So if you are multiplying by this vector, as we will see later in the course, if you are multiplying by this vector will only add the direction to what you are multiplying, and the magnitude will stay whatever the other thing had. And I'm saying directional derivative, right? We are going to take derivatives in multiple directions as we go on. It's simple stuff, but we like to make it sound like it's really special and spooky when they say, wow, space-time. Really? Space-time? Is it a tough concept? It's big words. No, they're not. It's x, y, z, comma, t. It's a 4-dimensional vector. It's nothing special, all right? You can check. Run the magnitude of u hat. If you get anything else but 1, we either made a mistake or broke mathematics. Right, so you know what to do. Square root of 3/5 squared plus 4/5 squared. And it has to work out to be 1. Well, it's 9 over 25 plus 16 over 25, which is 25 over 25, which is equal to 1. So we're good. All right, so to visit notation one more time and introduce now that we have the idea of what the unit vector is, we can also introduce the component notation for vectors. So we know that the vector u was using the spiky brackets ux, uy for 2 components. And now I would like to introduce another notation, because there are these special vectors I and j, which are the unit vectors in the direction of x and y axis. So unit vector I is going to be a vector 1, 0, and that's fixed in stone. And unit vector j, so these guys have the hats, is a vector 0, 1. So these are unit vectors. Unit vectors, you see that from the notation because they have hats. Also, if you run their magnitude, right, 1 squared is 1 plus 0 is 1. And square root of 1 is 1. So magnitude of each one of these is 1, the length. So now this allows us to write the vector u as uxi plus uyj. So the notation that we had before, we had as an example vector u was it 4, 3 or 3, 4? Whatever, 4, 3. So you can also write vector u as 4i hat plus 3j hat. So these are our new notation. And we like this ij notation because it is, you know, natural for us to think about. If you want to add vectors, then you add i's together and you add j's together. Again, this I has nothing to do with that complex I, right? This is nothing to do with it. Your I in Calc 3 is defined as unit vector 1, 0. Good. Is there anything else? No, that's it. That's pretty much it. Yep. Bye.